Hello everyone. Welcome back to my class. In last class, we discussed digital signals and positive negative logic. If you want to study digital circuits, you must know Boolean algebra. You already studied this topic in detail in your first semester course, Computer Fundamentals and HTML. Here I am not discussing it in detail. Let us revise what is Boolean algebra and what are the basic laws in Boolean algebra. Okay, let us start. Do you know this handsome guy? Who is this? Yes, it is George Boole, a famous mathematician. He is the man behind Boolean algebra. Here, we are discussing the fundamentals of Boolean algebra. These fundamentals are very important when you are solving Boolean expressions. Boolean algebra uses ones and zeros to represent data. Zero can be considered false or off. One can be considered true or on. In Boolean algebra, complement or dual form is obtained by changing every zeros to 1 and ones to 0, or every and with or and or with and. So, the complement of 0 is 1 and the complement of 1 is 0. The basic Boolean operators are and, or, and not. Here are some Boolean algebra laws. First one, identity law. That is, A dot 1 is equal to A. We can read it as A and 1 is equal to A. That means a variable ANDed with 1 is always equal to the variable. Similarly, A plus 0 is equal to A, or A or 0 is equal to A. That is, a variable ORed with 0 is always equal to the variable. Second one is annulment law. That is, A dot 0 is equal to 0 and A plus 1 is equal to 1. Third one, idempotent law. That is, A plus A is equal to A. A variable ORed with itself is always equal to the variable. In the same way, A dot A is equal to A. A variable ANDed with itself is always equal to the variable. Next one, complement law. That is, a variable ANDed with its complement is always equal to 0. That is, A dot A complement is equal to 0. A plus A complement is equal to 1. The fifth law, commutative law. A dot B is equal to B dot A. The order in which two variables are ANDed makes no difference. A dot B is same as B dot A. Similarly, A plus B is equal to B plus A. Sixth one, associative law. That is, A plus B plus C is equal to A plus B plus C. That is equal to A plus B plus C. It allows the removal of brackets from the expression. In the same way, A dot B dot C is equal to A dot B dot C. That is equal to A dot B dot C. Distributive law. A dot B plus C is equal to A dot B plus A dot C. A plus B dot C is equal to A plus B dot A plus C. Double negation law. Inversion of a term twice with result in the same term. That is, a double complement of a variable is always equal to the variable. I am not discussing more details of Boolean algebra laws because you all have studied it. All of these laws should be kept in mind while solving Boolean expressions. Now, Let's move to the next topic, logic gates. So, logic gates. You all know gates are the building blocks to create digital circuits. A gate is a combination of transistors and it performs binary logic functions. I hope all of you know basic binary logic functions and or not. I can define logic gate as it is a physical device which performs logic operation on one or more logical input and produces a single logical output. Please note, the logic gate can have more than one input, but only one output. Is it clear? A physical device which performs logic operations on one or more logical inputs and produces a single logical output. There are three elementary logic gates and some other symbol gates. Let us discuss all in detail. Each gate has a logic symbol and a truth table. Let us see. These are the types of gates we are discussing: NOT, AND, OR, NAND, NOR, XOR, XNOR and buffer gate. The first three gates, AND, OR, NOT, are known as elementary gates because all other gates are derived from these gates. So, let us move to NOT gate. First, we will see how we represent NOT gate. This is the symbol of NOT gate. Here, you can see there is only one input. In NOT gate, there is only one input and one output. Here the input is A and the output is X. That X is equal to A complement. X is equal to A complement. That is NOT gate performs the Boolean operation complement. X is equal to A complement. If A is equal to 0, A complement is equal to 1. If A is 1, A complement, that is X is 0. So, the Boolean expression of NOT gate is X is equal to A complement. And this is the logic diagram of NOT gate. Now, let's draw the truth table. Before drawing truth table, you should know what is a truth table. A truth table is a table having outputs from all the possible combinations of input. Left hand side of the table shows input. Here it is A. And the right hand side of the table shows output. In NOT gate, there is only one input A. So, only two different combinations for a single input. That is, A can be 0 or A can be 1. When A is 0, X, that is A complement is 1. When A is 1, A complement is 0. I want to show a real life example. How NOT gate used in a heater. Here, when the temperature is above 20 degrees Celsius, the input to the NOT gate is 1. That is on. When the temperature is above 20 degrees Celsius, the input is high or it is 1. What will be the output? The output will be 0. So, the central heating circuit is switched off. If temperature is below 20 degrees Celsius, then input to the gate is 0. That is off. Then the central heating is switched on. Is it clear? Next one is AND gate. The Boolean expression in AND gate is AND operation, which is represented using dot symbol. Now look at the logic diagram or symbol. This is the symbol. Here we have two inputs A and B and one output X, where X is equal to A dot B. This dot represents AND operator and it denotes multiplication. You can also have three inputs to AND gate. Let us say three inputs A, B and C, and the output is X is equal to A dot B dot C. Now look at the truth table. We have two inputs A and B and output X. As here there are two inputs, it is possible four different combinations of input. They are 0, 0, 0, 1, 1, 0 and 1, 1. We have to find out the result X. We have already discussed the AND operator in Boolean algebra. That is 0 and 0 is 0. 0 and 1 is 0. That is when the input A is 0, B is 0, X is equal to 0. Input 0, 1, X is 0 dot 1, that is equal to 0. 1, 0, output is 0. For inputs 1 and 1, the output will be 1. Here it is clear that the output is only high value when all the inputs are high. Now look at this example. All of you had heard about burglar's alarm. Burglar alarms are connected to a property via sensors and contacts. When they detect movement or opening of doors and windows, it produces a loud alarm. Look here. If we want to switch on the burglar's alarm, we put on the input alarm switch. So the input here is on or 1. If the device senses any intruder, the second input person sensor will be on. So both the inputs are now on and output signal to the burglar alarm will be on and it produces the loud sound. One of the inputs, alarm switch or person sensor, are off or both of them are in off state, the output will be off and alarm will not work. Is it clear, all of you? Next gate is OR gate. The Boolean expression of OR gate is X is equal to A plus B, or it can be read as X is A or B. Symbol of OR gate. This is the symbol of OR gate. As shown here, it can have two inputs and one output. Three inputs are also possible. Here A and B are the inputs and output is X. That is, X is A or B. For two input, there are four possible input value combinations. So look at the truth table. When A and B are 0, that is when both the inputs are 0, the output will be 0. When inputs are 0, 1, 1, 0 and 1, 1, the output will be 1. Hence, it is clear from the table that the output is high when any one or all inputs are high. Here is an example. This is for a doorbell. The doorbell wants to be rang when any one of the front bell or back bell switch on. This is possible through OR gate. That is all about elementary logic gates. On next lecture, we will discuss about derived logic gates. I think now all of you have a clear picture about elementary logic gates. See you on next class. Thank you.